This is not a secret, but we currently need oil and gas to produce energy. Thanks to oil, we can not only run our cars, but also heat our houses and pave roads, produce electricity, drugs, clothes, and many other good things. Hello everyone, my name is Elena Andrianova, and I am a PhD student at the University of Alberta. I am doing research in petroleum engineering. Canadian engineers are spending days and nights to find the most environmentally friendly methods of oil production. One of the big challenges of oil production in Canada is that the most of our oil is crude oil and bitumen, which is so dense that cannot flow without our help. Imagine honey. We have liquid or solid types. The same with oil. Conventional liquid oil can be produced easily, but unconventional bitumen is thick and cannot flow easily. So it needs to be treated before making possible to extract it. How we can help it to flow? We have two options to heat it, as in steam-assisted gravity drainage, or we can dissolve it by use of solvent, as in WebEx technology. These are the main methods of bitumen production. Unfortunately, they have drawbacks. The heating-based techniques inject hot steam under the ground, so a lot of water and energy are required, making the process not so environmentally friendly. Solvent-based methods are more ecological because they require less energy and water, but they work slowly, so are less profitable. The solution is the combination of heat and solvents. These methods are promising, but we still need to study them. How we can study these methods? The best way is computer modeling or simulation, when we make a computerized copy of an oil reservoir and test any desired production technique on it. If the model is small and simple, the simulation time is just seconds, but thermal solvent-associated techniques are quite complicated, so it can take days and weeks to run a single model. This makes it hard to perform testing. So my team develops a statistical upscaling method which will make models work faster under these complex conditions, but still stay accurate. By making it easier and faster to test oil production processes, we can help oil sand companies identify more environmentally friendly and ecological ways to produce oil that we all use every day. Using artificial intelligence techniques, including machine learning, my team trains computers to quickly and accurately simulate the real-world effects of changing parameters. This helps us to understand how different design, such as solvent types and flow rates, could affect the productivity of the well. This will minimize the environmental impacts of our current energy system, while our society makes the transition to a new energy system. Thank you so much for your attention.
Researchers predict the global energy consumption along with its associated CO2 emission will increase by at least 25% over the next 50 years. With increasing energy demand and awareness of global warming, the entire energy market is trying to transition from fossil fuels to renewable energy such as wind and solar power. Although the renewable energy sources are much more sustainable and environmentally friendly, they do suffer from the intrinsic intermittency. That is, their power output not only depends on location, but also time of the year or even time of the day. This results in an imbalance between the supply and demand in electricity. But what if we can build a giant battery that stores electricity when there's energy surplus and releases energy when there's energy deficit? This brings us to my research. My name is Yingjie. You can call me Jay. I'm a fourth-year PhD student at the Department of Chemistry at the U of A. My research primarily focuses on developing catalysts for battery applications, specifically zinc-carrier batteries. In addition to being low cost and extremely safe, zinc-carrier batteries can store 4 times as much energy as the current lithium-ion batteries. This benefits make zinc-carrier batteries an ideal candidate for stationary energy storage. However, the chemical reactions inside the zinc-carrier batteries are very slow. This lowers the potential and power available to the external device, also known as potential and power output. Therefore, current zinc-carrier batteries require platinum ruthenium as catalysts to speed up the reactions and increase the potential and power output. But the high cost and scarcity of this precious metal greatly impede the large-scale commercialization of zinc-carrier batteries. My project is to design and produce efficient and cost-effective catalysts as an alternative. The alternative catalyst I produced is a hybrid between hollow mesoporous carbon nanospheres, or HMC in short, and manganese oxide nanoparticles. both of which are much cheaper than a platinum ruthenium. Here is their electron microscopic image. The hollow structure of the HMC and the nanoscale size of the manganese oxide nanoparticles maximize the effective surface area of the hybrid, which ensures maximum interaction between the catalyst and the reactants inside the battery. To evaluate catalysts in zinc carrier batteries, we look at their potential and power output. When a catalyst is incorporated into the battery, higher potential and power output indicate a better catalyst, which we found here with the hybrid in comparison to the original HMC and the precious metal platinum ruthenium. We also found that the hybrid showed minimal discharge potential drop after 120 hours of cycling, indicating a highly stable material. This means that the battery can be recharged many times while still maintaining the same amount of energy storage capacity. In conclusion, not only does this hybrid catalyst reduce the cost of zinc carrier batteries dramatically, but it also exhibits higher potential and power output, as well as superior stability than their precious metal counterpart. This is an important step in making renewable energies more feasible and make sure we have the energy we need without the carbon dioxide we don't. Thank you for listening.
Global warming, climate change, greenhouse gas reduction, and energy transition are large and complex problems facing the world today. Given their magnitude and global impact, we often search for large-scale, top-down solutions to address these problems, overlooking that some answers may lie closer to home. Good evening. My name is Neelakshi Joshi, and I'm a postdoctoral researcher at the University of Alberta. My research deals with municipal and community-level climate action. The scale of cities and neighborhoods that we live in is important to understand, as this is where a large demand for energy is concentrated and where a majority of the greenhouse gas emissions emanate. Edmonton, the city where my research is centered, has one of the highest per capita greenhouse gas footprints in Canada, an unflattering 19 tons per person against a global average of 4.4 tons. However, the city has launched an ambitious energy transition plan to bring down per capita emissions to 3.2 tons per person by 2035 and aims for carbon neutrality by 2050. It plans to do so most by focusing on everyday issues like promoting denser neighborhoods with carbon neutral houses and encouraging electronic vehicles. My research analyzes how this transition plan addresses local contextual factors like the existing availability of and the reliability on fossil fuels, legislative and financial limitations, and a high culture of consumption. But do Edmontonians need to wait for the government to make changes in their carbon footprint? Based on my research into volunteer-led neighborhood organizations called community leagues, the answer is no. Certain neighborhoods in Edmonton and their citizens have initiated bottom-up action long ago through community leagues. They are adopting renewable energy for community buildings and investing in energy-efficient retrofits. Furthermore, volunteers regularly organize workshops and information sessions diffusing the understanding and adoption of low-carbon technologies deep into their neighborhoods. We are working in collaboration with these pioneer neighborhoods to develop long-term climate action plans to sustain and amplify this initial momentum. While neighborhoods and city-level efforts may seem small compared to large global problems, it is a combination of such small efforts that contribute back towards achieving national and ultimately international level greenhouse gas reduction targets. Thank you.
We all love summer. Imagine yourself driving on a country road, enjoying the sunshine, seeing the beauty of the landscape full of trees or crops. This reminds us about the beauty of our Mother Nature and inspires us to take actions to protect her better. However, what if I tell you that our daily life, especially driving, is emitting lots of carbon dioxide, which is adding burdens to our environment? Actually, over the past 60 years, the carbon dioxide content in the atmosphere has increased by over 30%, resulting in sea level rise, extreme weather, etc. One major contributor to this massive CO2 release is our consumption of fossil fuels, such as coal or gasoline. To help solve the problem, my research focuses on developing a novel fermentation technique for a very promising biofuel production, the alcohols. Specifically, I am developing the technique of SCF, self-cycling fermentation, for the production of the alcohols. Our research features 3 advantages. Number 1, we are not competing with food. SCF is designed to deal with various types of agriculture and forestry wastes, such as wheat straw, corn stover, sawdust, wood logs, etc. These wastes can generate sugars, and SCF can convert the sugars into alcohols. Number 2, high productivity. Current industry operates alcohol fermentation on a batch-to-batch basis, while SCF is a semi-continuous operation, which runs the fermentation much faster. As a result, we have shown that SCF can produce over 70% more alcohol each year compared to current batch method. Number 3, highly integrated and automated system. We have designed a software program to manipulate the fermentation process. With a computer, we can not only inspect but also control the fermentation process. This can significantly reduce the labor intensity, making it more financially viable for the industry. So far, we have demonstrated SCF in a small flask, a 5-liter bioreactor, and we wanted to scale it up to a 100-liter pilot level. With SCF, we are confident that we can help contribute to the protection of our environment. Thank you.
Hi everyone, I'm Maggie Cascadden, and I'm excited to present our research team's project to you. Our project is a life cycle analysis of novel materials and processes, and it's about the process of sustainable innovation. We're from the business school, so this project brings a business lens to the cool emerging technologies that other researchers are developing within the Future Energy Systems research program. The Future Energy Systems Initiative is all about understanding, designing, and evolving our future energy system so it looks the way we want. An important part of this is innovating solutions to clean up what's going to be left behind by our current energy system. In truth, this is a very difficult task, otherwise we would have already done it. And part of the solution will have to include technologies that haven't yet been fully researched or developed. Our team is specifically looking at the cool technologies that are being developed for constructed wetlands designed to clean up oil sands processed water. The first part of our study is to understand what energy, chemicals, and human power these technologies take to be manufactured, and the kinds and quantity of pollution they create. To do this, we're conducting something called a life cycle analysis. This is a method of accounting for all the inputs and outputs of a product making process, so you can add these up and see the full impact of that product on the environment. Inputs include things like water and energy, and outputs might include waste, heat, and chemicals. This is what it looks like for one of the technologies biochar, and as you can see here, there are many steps, and it's quite complicated. If you look at this other novel technology based on chicken feathers, it's even more complicated. The life cycle analysis software can generate estimates of material usage and waste products based on an inputted version of these maps. And it's important to conduct these kind of analyses so that we know the impacts of the technologies we're creating. That's our first major goal. After all, these technologies are not going to help us create the kind of future energy system we want if their production causes a worse environmental impact than what we're trying to clean up. In addition to all that, it's important that these technologies are economically viable if we want them to be real solutions that we can actually get out into the field and adopted by industry. So the second important part of our project is to identify which of these technologies have potential to be commercialized. Once we understand the life cycle of the new technologies, we can understand how much they're going to cost to produce. Our goal for this project are threefold. First is to identify which technologies are going to be the most beneficial for oil sands process water cleanup. Second is to identify which technologies are economically viable and commercializable. And ultimately, we want to help scientists and engineers who are working on the best technologies get their work out of the lab and into the field. Thank you.